So we start from the fact that we want to understand what is the meaning of many particle Hamiltonian and what is the corresponding wave function. So we have a rough idea that what exactly is the many-body Hamiltonian. Basically, when there's no interaction, we can write down the Hamiltonian in this fashion. Basically, we just sum over the Hamiltonian for individual particles. Okay, so we want to ask what exactly is the meaning of this expression by summing over the Hamiltonian for each particle. And we take a very simple example that is basically the free particle Hamiltonian, where summing over individual particle of the Hamiltonian that is of the form of a free particle. Basically, it contains only the kinetic energy. And in this expression, what do we mean by this momentum pi operator is that it only acts non-trivially on the Hilbert space of the ith particle, and it will act trivially on all the rest of the Hilbert space of the many-body Hilbert space. So we roughly have an idea about what is the meaning of this pi, or at least we have a more formal definition about what is this operator pi. So the next question we are trying to ask is how to describe the many particle wave function psi. So it is very tempting to say that we have the first particle, second particle, all the way to the ith particle, and we use this Hilbert space of the first particle to the ith particle to form the Hilbert space of our many particle system. Okay, and for each particle, it basically is described by a cap vector phi in each of the Hilbert space of the ith particle. It is very tempting to do so, but the problem is that when we try to write down the wave function in this way, one of the question is how to include the indistinguishability of our system. Okay, so that's the question that we are trying to answer. Now I'm trying to use this simple example and try to get it back to the more general consideration. Okay, so for non-interacting systems, the total Hamiltonian is the summation of the Hamiltonian of individual particle, and the Hamiltonian of the ith particle is represented by this. And because of the laziness, or because we want to keep our notation simple, most of the time we only write down this hi hat. But what it really means is that this operator needs to act trivially on the rest of the particles and only act non-trivially on the ith particle. And if we try to write down the eigenstate of our total Hamiltonian, which here this n is the index for the many-body energy spectrum. Okay, so the eigenstate should be, or we are trying to ask how to express it. A very intuitive idea is that maybe the first particle is sitting at some energy of the first Hamiltonian at energy En1. And maybe the second particle is sitting at the energy of En2. Okay. And dot, dot, dot. And the I minus 1 particle is sitting at the energy En I minus 1. And the nth particle is sitting at energy Eni. And the I plus 1 particle is sitting at energy Eni plus 1. Okay. And our question is, or to some extent, we can ask, if this is the state, what kind of energy it will give us. We can just apply the total Hamiltonian on this total wave function with energy En. And because we know our non-interacting Hamiltonian can be written in this fashion, right? And we also know the ith particle Hamiltonian apply on the eigenstate with energy Eni will give us the energy Eni of this corresponding state. So when we apply this operator to the total Hamiltonian, let's take this ith particle in particular, we'll find that the Hamiltonian of the ith particle will act non-trivially on the Hilbert space of the ith particle. And the rest of the operator will act trivially on the other Hilbert space of the rest of the particle. So when we apply this Hi to this En, for each of the Hi, it basically, you will contribute a term that corresponds to the eigenenergy of Ni. Okay? And now we are summing over all the particle Hilbert space. Therefore, when we apply this operator to this total eigenvector En, we basically get the total energy, which is En of our system. Okay, so indeed, if we construct the En in this fashion, and when we apply Hamiltonian Hi on this En, it will return the correct single particle energy. And for the non-interacting Hamiltonian, the total Hamiltonian will also give us the correct total energy En. Okay. So the question is, this is not a complete answer as we discussed. This is a distinguishable particle setting. So the question is how to include the indistinguishable property. Okay. So as what we have done previously in the two-particle system, we ask, can we symmetrize or anti-symmetrize the wave function. So before we write down the way to express this wave function, let's try to define something called permutation. Let's use P to denote the element of a permutation group. The idea of permutation is simple. You basically just try to shuffle the object and try to get all the possible orders of this object. So that's the idea of permutation. So for example, if we have 3 objects, let's label it by 1, 2, 3, and there will be 3 factorial or 6 different ways to arrange these 3 objects. So for these 3 objects, the permutation group actually has 6 elements, and every element corresponds to one of the permutation, which correspond to the possible arrangement of these 3 objects. Okay, and for each permutation P, we provide a number to characterize its property. So basically, we use P bar to denote the number of swaps to get permutation P to an ascendant order. So what does that mean? Suppose we have a permutation, which is in this 3 object case, suppose it is 2, 3, 1. Okay, this is the permutation we have. So P bar is basically the number of swaps that we need to get this particular permutation 2, 3, 1 into ascendant order, which is 1, 2, 3. So how to get that? So we can swap once to swap 1 to the middle position. So we have 2, 1, 3, and we swap the second time, then we got 1, 2, 3, and that is the goal that we want to get. So for this particular permutation 2, 3, 1, the P bar, which is the number of swaps in order to get to 1, 2, 3, is actually 2. Okay. So using the permutation and P bar, we can write down a very generic expression for a symmetrized or anti-symmetrized wave function. And as you already learned in the last lecture, the symmetrized wave function corresponds to the bosonic wave function, and the anti-symmetrized one corresponds to the fermionic wave function. So let me just use this eigen wave function to express it again. So here is the many-body wave function for the boson or fermion, represent in this cat notation. The many-body wave function will be expressed like this. Here, summation over P means we are summing over all the possible permutations. And here, we introduce a parameter eta equal to +1 or -1. And the reason for that will become apparent a little bit later. And this eta is raised to the power of P bar And here P bar is defined as we described here, that it is the required number of swap in order to get to the ascendant order permutation. And then we write down the corresponding energy of the of our system. So here, this P of 1 means that the first element of the corresponding permutation in this summation. And P of 2 will be the second element of this particular permutation. And N1, N2 are the corresponding single particle quantum number for the eigenenergy. And in this expression, eta is chosen to be +1 for bosons, and eta equal to -1 for fermions. Okay. So let's try to take a simple exercise for the 3-particle case. For a particular element of the permutation group, suppose we have a permutation of 2, 3, 1. Okay. Then we can ask what is the corresponding term when it is for boson and for fermions. Okay. For bosons, we have eta to be +1. And the question is, what is the corresponding number P bar for this system, for this permutation? As we have tried, we know that P bar for this permutation is actually 2. So if we look at this expression, the corresponding term in this summation is +1 to the power of 2 times the cats E and 1, and the first element is 2 and 2, and the second element is 3. The product E and 3, where the last element is 1. So this is one of the terms in this summation for bosonic system. For fermionic system, or for fermions, we have eta equal to -1, but because of this permutation is with the P bar equal to 2, this -1 raised to the 2 actually will be identical with the boson case. Again, we can write down the corresponding cats. Okay. So this is one of the terms. We can ask what are the terms that could be different, because here, because of this P bar equal to 2, whether it is boson or a fermion doesn't matter, because +1 -1 raised to the power of 2 will always be the same. But as we know, for these 3 elements, there are actually 6 different permutations. So let's try to pick another permutation P prime, which is 3 to 1. So for this permutation P prime, the P prime bar is equal to what's the number we need to do? Let's try to see. So in order to make it into the order that we want, we need to shift 3 twice to the most right-handed position. And then after we perform that, we need to shift 2 with 1 in order to get the right order. So P prime bar is actually 3. So we need to have a term that is going to be proportional to eta to the cube. So for bosonic systems, this term is plus 1 to the cube, which is not super relevant because plus 1 raised to any power will always be plus 1. So okay. But for fermions, this term will make a difference. It will be minus 1 to the cube, which give us a different space vector when we try to form a linear combination or when we try to anti-symmetrize the wave function. Okay. So that's the effect of this construction when we include all the permutations. For those, you need to perform even number of swaps. We call this the even permutations. And for those states that you need to perform odd number of swaps in order to get it ordered, we call it the odd permutations. So in the expression of the wave function, the bosonic wave function is fully symmetrized because no matter what kind of permutation you use, you always have a plus sign. But for the fermionic system, the case is a bit different. That when you perform the odd permutation, the wave function actually have a -1 factor. Okay. In this summation. So one question is, what is the energy for this individual system? And it turns out that if we try to apply the total Hamiltonian, in this case is H1 plus H2 plus H3. And when we apply the Hamiltonian to this, no matter it is boson or fermion, naively, if they are all distinct, we should get the energy of En1 plus En2 plus En3. Okay. And the reason that it is so is because when you apply the Hamiltonian on the cat, basically each Hilbert space is not disturbing the other Hilbert space. So eventually what you will get is the sum over the 3 eigenstate, N1, N2, and N3. Okay. So every term basically will have the same energy. So that's why we still have the correct eigenenergy behavior that we want. But also, because we include this non-trivial -1 factor, it takes care of the fact that whenever we swap the position of our wave function, it will pick up the corresponding +1 or -1 sign. The reason is, as usual, when we want to write down the wave function of a single particle state, we use broad operator X and inner product with this wave function phi. So in this many particles case, you use bra of x1, x2 to xn, which represent the coordinates of these n particles with the wave function that is symmetrized or anti-symmetrized according to the expression we give here. And you can see that because of the symmetrization property, when you swap x1 and x2, basically the symmetrized wave function will be invariant. And whenever you consider a fermionic case, whenever you swap the x1 and x2, what is going to happen is that you will introduce additional swap in this wave function permutation, and it turns out that you will pick up a additional -1 sign whenever you swap the x1 and x2. So that will give you the corresponding bosonic or fermionic wave function. Okay. And you can also ask, if we are thinking about the many-body quantum states in this fashion, how to see the Pauli exclusive principle. And the idea is that if you choose one of the n to be the same, let's take our 3-particle case, for example. Let's choose the quantum number n1 is equal to n2. For fermionic case, you will find that you will have one permutation. For example, for this particular permutation, we just randomly pick one, and the corresponding operation will give you this expression for this particular now n2 is equal to n1, so I'll just write n1. Okay, this is one term, but because there's always another permutation that is related to this permutation by swapping this these two, and the corresponding p-bar number will be 2, because there's a one time less for you to permute this permutation group. And n1 equal to n2. Okay, so you can see that these two terms will basically cancel each other. So similar mechanism applies to all the permutation group elements, and you'll see them kill each other one by one. So eventually you got the conclusion that for fermions, you cannot have two particles occupying the same state. And that is the Pauli exclusive principle. Okay. So are there any questions right now? Okay. So if not, I'll continue. So for those who want to have a more detailed discussion about this many-body wave function, you can find related description in the chapter 1 of Nedry and Nolan. And the book is called Quantum Many-Particle System. Okay. So so in this discussion, I'm just using the En to label the single particle states. So let me try to express what I meant using simple pictures. Okay, so let's use this simple picture to represent the spectrum and the Hilbert space of the first particle. And somehow did it a little bit tilted, but please ignore that. And we have m particles, so the Hilbert space should be labeled by the particle 1 to n, and the Hilbert space is formed by the real products of those individual particles. And here, this E1 to E0 to E1 is basically the single particle energy. Okay, and so this is just a pictorial expression for this kind of state, because if we just think about one of these component, it basically tells us that we have energy En1 and energy En2 ... to all other possible configuration. So for example, if for the first particle it is occupied by this state, then we need to include this particular energy into our summation. And if it is for the second one, it might occupy a different pattern and things like that. Okay, so this kind of expression is for a generic non-interacting many particle system. Okay. Of course, as we mentioned, in order to describe the real wave function for the bosonic or fermionic wave function, we need to symmetrize this wave function using this construction we just gave. And by the way, there's a 1 over n factorial to the square. That's just a normalization factor that I forgot to mention, because for each permutation there are n factorial of such terms. So each one of them should contribute 1 over square root of n factorial. Okay. So this is for a generic non-interacting many particle system. And here we just use 0 and 1 to represent the eigenstates. So we can ask, how about for a free quantum gas system? Okay. So we know the single particle spectrum for the free particle is like this. Basically, this curve is k squared divided by 2m. And as we mentioned, we have discrete case to label the eigenstates. because now now the momentum is a good quantum number to describe the single particle wave function. So very similarly, because we have m particles, so the full Hilbert space is supposed to be the tensor product of these individual eigenstates. So what do I mean by that is for bosons, we should symmetrize the cat representation the first particle, second particle, all the way to nth particle. Okay. And for fermions, the only difference is instead of symmetrize it, we actually anti-symmetrize this expression. Let me try to arrange the spacing. Okay. And because of this anti-symmetrization condition, we have the requirement that kn1 or kni cannot be equal to knj. I should make my notation consist. Okay. And this is the Pauli exclusive principle. Okay. So at this moment, we can see a very different behavior. If we are at the zero temperature limit, that means we don't care about the entropy, and we only care about the minimize the energy. We can ask, what is the ground state energy? And the ground state energy for boson at t equal to 0, to some extent is trivial, because we can basically, for bosons, there's no restriction about how to choose this case. So we can always choose k such that individual energy is minimized. So for bosons, the ground state energy is simply the number of particle times the energy at k equal to 0. Okay, and for this particular dispersion, it will be 0, and the wave function is just symmetrized. Okay, and for fermions, the situation is very different, because now we have the constraint. Oops. that now we have the constraint that K cannot be identical. Okay. Therefore, the rule to construct the many-body wave function tells us that we need to fill the energy levels one by one. Okay. So what that means is that once we put the first particle at the lowest energy, the second particle cannot be occupied the same state. So it means that we need to put it somewhere with a higher energy. Okay. When we put it somewhere in a higher energy for the second particle, the third particle, we need to consider the energy configuration that is not occupied by these two previous particles. So we will need to put it somewhere with lower energy. So in that sense, when you consider the fermionic wave function, it tells you that you are actually gradually fill in the single particle spectrum until you use up all your m particles. And the corresponding energy when you fill your all your particles in this single particle spectrum is called the Fermi energy. Usually it is denoted EF. So EF is basically the highest energy, the highest field energy. Okay. So to some extent, for fermions, the idea is like once you occupy this guy, you can only occupy the rest, or in some other different fashion. Okay. So are there any questions so far? Okay. So now we are going to write down the let's see. We are now trying to ask how to construct the corresponding partition function of the quantum many-particle system that we are interested in. So here's the question we are posting. Okay. So here we assume we have fixed particle number to be n first. Okay. So this condition is actually not super important, but I just want to have an initial idea about how to construct a partition function for n particle system, n particle quantum system, and then we will try to relax this condition and see how things will change. Okay, so in the above discussion, we noticed that the only, or maybe the most important difference between bosons and fermions is that in bosonic system, we are allowed to form a configuration such that everybody is basically sitting at the same state, right? For example, for the ground state of bosons we just discussed here, we have all m particles sitting at k equal to 0 mode. However, for fermions, it is not the case because of the Pauli exclusive principle. So we can try to switch our notation a little bit. At first, we can say that we have one particle sitting at k naught, and maybe the second particle is sitting at momentum k1, and maybe the third particle sitting at k2, etc. Okay, and maybe we have nth particle which is sitting at certain momentum k. So if we try to use another expression which is called occupation representation, instead of listing all the momentums or the possible occupation of the state, we try to ask how many particles are sitting at the momentum k naught. Okay, so we have n k naught, which represent the number of particles sitting at momentum k naught. And we can also ask how many particles is sitting at momentum k1, and how many particles is sitting at momentum k2, etc. And this occupation representation is useful because we don't care about the label of the particle. And the reason for that is because we are talking about, or we are discussing about the indistinguishable identical particles. That's why we have this fermion and bosonic wave function. And because they are indistinguishable, all we are able to identify is some particles, maybe 3 of them are sitting at the ground state, but we don't know which one is which. So we provide a label for each one of them. So this occupation representation did not actually lose anything. And in the contrary, it actually captured the most important information for this indistinguishable quantum particle. And this occupation number representation is very important when you are discussing or learning more many particle formalisms. It is closely connected to the idea or the formalism which is called second quantization. Okay, and maybe the simplest formalism for second quantization is the simple harmonic oscillator that we have discussed about, because the Hamiltonian can be written as h bar omega times a dagger a plus 1/2 for this single mode operator. And this a dagger a, if you try to represent that in a different fashion, you can express it as the number of harmonic oscillator quanta occupying this particular mode of h bar omega. Okay, so why this occupation representation is going to be useful? Because if we write down this occupation number representation in this way, then the total number is constrained to be the summation of all the possible momentum kj. Okay, so this is the constraint for the system with fixed particle number. So using this representation, we can write down the canonical ensemble for n particle system, quantum system. Okay. So so I'll just write it down. So here I try to make a abstraction that even though we are using the free particle as an example, and we use nkj to label the states, but actually k can be anything. So I'll just suppress the index kj into just j. Okay. So if we use this notation, the partition function is that we need to sum over all the possible configurations, or we can we need to sum over all the possible occupation number, and we impose a delta function, which is like the if statement in our calculation. That is by the way, in addition to these relevant quantum numbers, there are still some other internal degrees of freedom that's called alpha. So usually it is like the spins. Okay, and the constraint is that we sum over all the possible occupation number such that the summation of this occupation number is equal to the total particle number n. And then the Boltzmann factor is, as usual, minus beta times the total energy. Now we have sum over all different internal degrees of freedom and the corresponding eigenenergies. In this case, it's a free particle, and at each free particle level, which is labeled by this momentum pj, there's an occupation number nj alpha, and alpha is just the internal degrees of freedom for this system, such as spin. So it is just doing nothing, just providing additional index. Okay, so the reason we put nj here is because, as we already mentioned, for bosons, it can be any kind of integer as long as it satisfies this constraint. But for fermions, this nj can only be 0 or 1. Okay, so this is just a example, but if we try to think about the logic, actually here it doesn't need to be the free particle. it can be any abstract idea of a single particle energy level, EJ or epsilon J. Okay, so let's just put it aside and try to take a look about what is the expression for the grand canonical ensemble for M particles. Okay, so the partition function for the grand canonical ensemble can be constructed easily from the canonical ensemble. So what we need to do is we just need to sum over all the possible particle number and times a additional factor eta times mu n. Okay. Are there any questions? Because I'm hearing sound. Okay. So if not, let's continue. So yeah, so basically, that's the expression for grand canonical ensemble. So if I try to write it explicitly, it will look like this. By the way, if we sum over all the possible n, because of this delta function, we will put summation nj into this exponential and replace the n with summation nj. Okay, so if we do that, eventually what we will get is we need to consider all the possible occupation number, including the internal degrees of freedom, and we will have an exponential factor minus beta times sum over internal degrees of freedom alpha and j. And here the kinetic energy is pj squared divided by 2m. And because now we have this summation nj alpha multiplied with the chemical potential, we can put it together with the kinetic energy. Okay, and at this moment, there's no constraint about the nj, because now we sum over all the possible total particle number n. So in general, that's the expression for non-interacting particles. And again, I try to emphasize that even though I'm using the free particle as an example, you can take this kinetic energy as some kind of single particle energy, because the system is basically non-interacting. So now the question is how to simplify this expression. And here we are going to use the fact that non-interacting system provide a special structure that the partition function can be factorized. Okay, so let me try to write it out. So this summation can actually be converted into a product of J, which label the corresponding single particle eigenvector, and alpha, which correspond to the internal energy. But now it is a product of an infinite series of nj alpha. And this infinite series is actually a geometric series that you know how to deal with. Okay. And as I mentioned, you can always replace this energy by some kind of, abstract idea of single particle energy. And as I mentioned, this summation is an infinite series. Here we'll just express it by this special function theta of epsilon of p alpha minus mu. Okay. And this is just the infinite series of this exponential factor. Okay. So because of this simplification of the non-interacting particle assumption, we reduce the many particle partition function into analysis for a single particle problem. And for a single particle problem, this partition function can be evaluated easily, because for fermions, the occupation number n can only be 0 or 1 for this single particle system. So this summation reduced to, let me try to express it. And this is for fermion. And for bosons, because n can be anything, so if this exponential factor is smaller than 1, which means that we can sum this infinite series and it converges, then eventually we will have this function zeta epsilon minus mu to be expressed like this. Okay. So it will be quite convenient to just combine these two expressions into one expression that is, can use this thing as eta, and eta equals to +1 for boson, -1 for fermion. Okay. So that's basically the general expression for the partition function. So if we try to take the nature log for this grand canonical partition function, eventually what we will have is okay. And here I'm going to sum over these internal degrees of freedom. Most of the time, this internal degrees of freedom is related to spin. So it will contribute some factor like 2s plus 1. And we will have this minus eta as always. And we sum over all the single particle energy J. Here I should be a little bit explicit that this energy epsilon is related to J. Okay. So here I want to mention one thing that from quantum field theory with locality, causality, and Lorentz invariance, one can make the connection that fermions must be something with spin s, which is half integers. And bosons will have integer spins. Okay. So at this moment, we are able to perform some more generic expression for the free particles, because for the free particle, the energy is a function of the momentum. For the single particle, it will just be p squared divided by 2m. And this summation j, to some extent, will be replaced by summation over all the momentum. And in 3 dimension, if we consider the continuous limit, it will be related to this particular integral. Okay. And here, if we assume z, which is the fugacity, then we can further simplify this nature log of the grand canonical partition function as, okay. So as usual, we know that it is good to replace the integral using dimensionless variable. In this case, we can define p tilde to be p divided by square root of 2m kbt. Okay, and then we will get the partition function that looks like this. And here we assume the integration over momentum is isotropic, so this thing will be replaced by this integral. And then when we change our variable to this dimensionless parameter, then Okay. So here I'm not going to do too much about the detail right now. I'll just point out some direction about how to proceed, and in the next lecture I'll be more specific. The idea is that you can expand this nature log function into infinite series. Okay, and once you do that, you'll notice this integral will be related to a bunch of Gaussian integrals. That you are able to perform term by term. And once you do that, you will see it is related to a special function. Here I'll just write down the form of the special function. And here alpha is the parameter for this special function. So for the grand canonical partition function, after you perform these steps, you will get this expression. And this lambda is the thermal WE wavelength that we should be familiar. And we still have the internal degrees of freedom, 2s plus 1, and minus eta from the statistics, whether it is boson or whether it is fermion. Okay. So from this expression, you can derive the expectation value of the particle number by taking derivative of the nature log of grand partition function with respect to beta mu. And if we use fugacity, it will look like this. And the important thing is that once you perform this differentiation, you will see something. Of course, there are some coefficient, but the integration will looks like you are counting over all the possible states labeled by P. But there's a function that's like you are averaging over the occupation number for each mole P. And this occupation number average will be different for bosons and fermions. And turns out this occupation number MP will look like this. Or you can simply use use etas to represent these occupation numbers. Okay, so I think that's the general discussion for quantum particles. So I think today we basically want to give you a very how to say pictorial picture about what do we mean by when we have a quantum many particle system, because I think in the most cases we don't discuss the many particle Hamiltonian and many particle wave functions in detail, but to some extent, in order to really understand what we are doing, we need to have a minimum exposure to this concept. And the key is that when we talk about indistinguishability, Hamiltonian itself, of course, is indistinguishable because we always care about the total Hamiltonian. So whenever you permute the particle number, this Hamiltonian will not change. But the subtle part is about the wave function. So in order to include the indistinguishability, we go through a series of arguments, and we said that the simplest way to symmetrize your wave function is by introducing this idea of permutation group and characterize the element of permutation group to be even permutation or odd permutation according to the number of operation one needs to perform in order to get the permutation into an ordered permutation. So that's the symmetrization process that we introduced here. And from there, it is quite general. You can understand why bosons can occupy the same states and why fermions cannot. So you can explain the Pauli exclusive principle even for n particle system. So you don't need to rely on the two particle example, even though it is the simplest non-trivial one. And then we said that that picture is very useful because for non-interacting system, basically this is the generic structure, and we apply that to a free particle system, and we realize that for free particle system, if it is a bosonic system, it can be occupied in the lowest energy, and actually this state where all the bosons stay in the same energy level is called the Bose-Einstein condensate. We will discuss that a little bit later. And for fermions, because of this exclusive principle, we will need to fill all the particles into our system such that they don't violate the Pauli exclusive principle. And it turns out that the energy can only increase when we try to add more particles. And one of the characteristic energy for our system is the Fermi energy. It corresponds to the highest field energy level for the M fermion system when the temperature is equal to 0. Okay. And then we said that we can try to use a different representation, which is the occupation representation. And this occupation representation is very useful for understanding the second quantization, which we don't have time to address a lot, but it is very useful for us to construct the corresponding partition function. So we construct the canonical ensemble and the corresponding partition function for fixed particle number n, and generalize it to the grand canonical ensemble. And we found that because the system is non-interacting, we can factorize our partition function, and this reduced the problem to study a single particle problem. And once we found this simplification, it dramatically simplified the calculation of the partition function because the infinite series for fermionic system actually contains only 2 terms. And for bosonic system, because it is a geometric series, we can have a closed form expression if this ratio of the geometric series is smaller than 1. And then we got this very generic conclusion that you can express your partition function using this zeta function. And then we use a very special example, which is the free particle system. And we argue that if you try to perform the integral carefully by expanding this log function and perform the Gaussian integrals term by term, you can express your partition function, your grand canonical partition function, using this phi alpha function, which is the polygon function. And similarly, you can express the occupation number and the total particle number through this relation. And the important thing is about the occupation number, which is quite generic for these non-interacting systems. And they are basically the Bose-Einstein distribution function and the Fermi-Dirac distribution function. So that will be today's lecture. And sorry for going over time and the internet connection problem. So if you have any question, you can stay online and ask me. And if not, that will be today's lecture. And please remember to turn in your homework. And we will have a new homework posted soon. And that's it. Have a nice weekend.